Alright, so from your Ohm's Law section, you should now be familiar with path of least resistance. If we create two paths in front of our current, one with less resistance and the other one with more resistance, our current will always distribute itself within these two paths accordingly. So the path with the least amount of resistance is going to get the most amount of current. Now what if our path has zero resistance? In that case, we are basically telling our current, hey, we're giving you a path with no resistance back to our voltage source. So at this point, our current has no excuse to take the path with any kind of resistance to it. So it will always take the path of zero resistance. Whereas in an open circuit, we're just saying that, hey, resistance is so large, infinite, that no current can pass through that path. So let's experiment what's going to happen if we create opens and shorts in different parts of our circuits. First scenario, I'm going to create an open over here. So when my circuit, when my current that's generated from the voltage source reaches this node over here, it has a path that leads to R, and it has a path that leads to this open, which is like an infinite resistance. So we know that where there's an infinite resistance, there is no current. So current will completely ignore this path and it will go through our resistor down here. So our new circuit will look something like this, where we can now ignore the part of the circuit that's been opened and analyze this circuit alone. For our second scenario, let's create a short in the same location. So I'm going to short the circuit from here to here. And this can be a little bit tricky. When my current reaches this node, it has three paths to take. It can either take through this resistor, it can go through the short, or it can go through this resistor up here. If my short had a little bit of resistance, then this current would distribute itself among these resistors. But now, since my short has zero resistance, then my current will completely ignore path 1, completely ignore path 3, and go through the short. So my new circuit will look something like this. I have my battery source, I have R, and then my short. So if you're gonna reason this in a better way for yourself, you could do this. You could say my short has two terminals. Terminal 1 is located on this node in blue, and terminal 2 is located on this node. So I can move my short without changing my terminals. So I could literally say that that short is just equivalent to this short over here. So now it's much more easier to see why, when current reaches at this point, is going to completely ignore these two paths and go through our short. And what happens if we create an open over here? So When current reaches over here, it reaches to a infinite resistance. And again, current through infinite resistance is 0. So then there is no current passing through that. So my I is 0. So there is no current anywhere. And my circuit will look something like this. And this circuit is not complete and has no current. So because of that, because I have no current, then I won't have any voltage drop across these two resistors. I won't have any I times R. So whatever potential that my battery provides, if I connect a voltmeter, I will see that same voltage, V1. So what we see over here is an open circuit with two resistors and a potential difference of V1 across it. And for the last scenario, we're just gonna short the first two resistances. So when current reaches up here, it sees the path of no resistance, so it's gonna take that path. And once it reaches here, it sees two resistances, so it's gonna distribute itself. We're gonna have I2 and I1. But our circuit will look something like this now, where I'll have my battery and I'll have two resistors in parallel. Why in parallel? Because these two resistors share two terminals together now. This is terminal 1 and this is terminal 2, which is common for both resistors. Now let's discuss what's going to happen if we short and open ideal voltage and current sources. So I have ideal sources. First scenario, I'm shorting my ideal voltage source, and the current that I'll introduce in this, I'll denote it with I. And if you remember, we said that short is same thing as a resistor with 0 ohms resistance. So then my I is going to be V over R using Ohm's law, which is also equal to V over 0, which is equal to infinite amps. And my power is I squared R, which is also equal to infinite. So with an ideal voltage source, a short would result in infinite amount of current and infinite amount of power generated. But that's not the real case in life. Same thing with the current source. If you have an ideal current source, and let's say it was connected to a circuit and we just opened it, well, an open is the same thing as a resistor with infinite ohms. So now the voltage across this resistor is going to be I times R, which is going to be I times infinite, which is now infinite volts, infinite potential, and therefore our power, which is V squared over R, will also be infinite. So the thing is that these guys are ideal sources, but in reality, we're dealing with practical sources. So this is how practical sources look like. Practical sources have some internal resistances associated with them. And if I short a practical voltage source, what's going to happen is that now my current I will be limited by this internal resistance over here. So my I will be V over R source plus our short resistance, which is 0 now, which is going to be V over RS. So now our current is a value, it's not infinite anymore. Depending on the value of RS, it could be a very large number, but still, in practical cases, our current is limited. Same thing with the current source. If I had opened my current source, and that means connecting it to an infinite resistance, now the voltage across it is going to be I times R equivalent, and parallel resistances are going to do this. We're going to have I times R source times infinite divided by R source plus infinite. So this is going to be equal to infinite, and it's going to cancel out with this top infinite, and we're just going to have I times RS. When we connect a practical source with internal voltage of Vs and resistance of Rs to a load, depending on how large this created current is, the terminal or output voltage across this RL would be smaller than our source resistance. Why? Because we have our voltage divider equation. So voltage divider equation says that VL is going to be Vs times RL over RL plus RS. So what's happening here is that if I have a very large current, that's going to result in a very large potential difference or potential drop across my source resistance. So it's going to result in a large IRS, and that's going to limit the amount of potential that reaches to the load. So this graph over here is modeling how the output voltage of a practical source would look like. So the higher current we have in our circuit, the larger potential drop we have across our source resistance, and that results in a reduced amount of V out.